Okay, welcome to the next lecture on multiple view geometry. We are in the part 6 of the slides, and the topic is the reconstruction from multiple views. And so the idea is to generalize what we've learned for two views to multiple views. And you may remember in the two-view case, we had what was called the epipolar constraint. Epipolar constraint. And then that led to the 8-point algorithm, among other things. And we also talked about variants of this 8-point algorithm for the assumption that we study what we observe a plane in 3D. We can have a planar epipolar constraint or homography constraint, and then we have a similar algorithm called the 4-point algorithm. And what we want to study now is once we move from two views to the M view case, so the case that we have 3, 4, 5 or more views of these points in multiple images. The question is, what does this generalize to? What is the generalization of the epipolar constraint for the multiview setting? And similarly then, what is the generalization of an 8-point type algorithm for the multiview setting? And the idea of these algorithms, just to remind you, was to try to decouple the motion estimation from the structure estimation. So we have our 3D scene, we observe it from different views, and so what changes from one view to the next is the camera is transformed, so there is a rotation and translation of the camera happening, and that is unknown, and in addition the 3D location of points is unknown. And we saw already in many ways that how you phrase the optimization problem, how you specify the unknowns, you can do different things, but one is the unknown is the depths, let's say, with respect to the first image, lambda 1. And so for a point xi, then we have lambda 1i, and we have rotation and translation between the different cameras. And the idea of the epipolar constraint is it was a constraint that separates the 2D observed coordinates. It separates the motion of the camera from the 3D location in a way that we get a constraint coupling the 2D coordinates with the camera motion, with this essential matrix. So the epipolar constraint, if you recall, was x2 transposed E x1 equals 0, where this is little x1, this was little x2, and E was the essential matrix that was T hat times R. So a matrix containing only the camera parameters. And the 3D location of points, the whole 3D information is no longer in the constraint. And the question is, can we do similar things in the multiview setting? And it turns out that yes, we can. And there are different ways to get these constraints in, and they've been studied in various papers in computer vision, and then the goal is to eliminate these constraints systematically. And that leads to a complete set of conditions, and then we can use these conditions for estimating the camera motion. And we saw that the way this approach works is that with the epipolar constraint and the 8-point algorithm, you first estimate the camera motion, and once you have the camera motion, you can estimate the 3D location of points in these depth values. There's another set of constraints on the depth values for a given camera motion. And one is called the motion estimation, the camera motion, translation, rotation, and one is called the structure estimation. And this is why in computer vision the problem is known as structure and motion. In robotics it's typically called SLAM, or more specifically for cameras, visual SLAM. Where SLAM, as you may remember, stands for simultaneous localization and mapping. Localization is what we call motion here, the camera, and mapping is building a 3D map, means estimating the 3D coordinates of points. So this is just to remind you there's different terminology that people use. Now we focus on the multiview setting, and so we consider the projection. We had projection equations for each image, and we can stack them into a whole set of projection equations. And we'll write this compactly, and one of the things you'll see a lot of matrices appear in the following slides. It's not necessarily very complicated, really. It's typically just that you group all the information you have and write it in an as compact way as possible. The reason why we do that, for example, we have a single little equation with 4 symbols here, is not to hide information but to simplify and condense information. Often with introducing new notation in mathematics, you can simplify things in a way that the structure of the problem becomes more transparent. And this is the goal here. So we have the projection equation. Just says, if you read the first equation, it says lambda 1 x1 is pi 1 times large X. So the equation is lambda 1 times little x1 is pi 1 times large X. And pi 1, to remind you, includes the rigid body motion to the first camera and the generic projection. So in this case, pi 1 would be the generic projection, pi times g1. If you're working in the coordinates of the first camera, then g1 is just the identity. It's just a unit matrix. And so pi 1 is just the generic projection. But in general, for image I, we're going to have lambda I xi is pi I, and then we have gi here. And in the general case, gi is going to be the transformation to the coordinates of the ith camera. So that is the equation where lambda I is the depth. So that would be the depth with respect to image I, and then we have the camera transformation. And so if you look at the structure and motion problem, this is the projection equation, and what's useful is also to keep track of what are the knowns and what are the unknowns in the equation. The known parameters here are the 2D coordinates. These we have observed. We assume we have the 2D coordinates of a single point in m images, x1 through xm. So these are the 2D coordinates of that point in all the various images. So m is now the number of images that we consider. The depth parameters, this is the depth with respect to the lambda 1 with respect to the first camera and lambda m with respect to camera number m. These depth parameters, they are unknown. That's the structure, the 3D information. This is unknown. What's also unknown is large X, the 3D coordinate vector, and what is unknown is the projection matrices. These contain the camera motion. So we have the 3D information in here, and we have the camera motion here. And in general, you would typically put yourself in the coordinate system of the first camera. So you would say, this is my origin, and this is my coordinate system, the z-axis pointing in the direction of my camera. In that sense, then pi 1 would just be a generic projection matrix. And so we can write this compactly. We call this matrix I, because it's the image observations in the image. And then lambda vector is the depth values with respect to all the different images. Pi is that it looks like a vector, but these are matrices, so it's a stack of matrices of all these projection matrices modeling the projection of a 3D point in homogeneous coordinates into the image 1, 2, 3, and 4. And X is then, and so X is the 4D vector representing the 3D point that we look at. So we're just looking at a single 3D point in multiple images, and this is the projection equation. And pi is called the multiple view projection matrix, so you can give names to everything. And typically, as usual with names, you want to give names that are intuitive. Here it models the projection for the multi-view settings, for M views. And I is called the image matrix, so these are the 2D coordinates on the diagonal, and there's zeros on the off diagonals. So this is just putting all the equations into one system of equations, a linear system. Unfortunately, with this linear system, it's not like a linear system that you can directly solve for the unknowns. You could solve it for lambda if all the rest was known, but here it's a linear equation system where there's almost nothing known, or very little. The only thing that is known is I, the rest is unknowns. But it is some constraint, at least. It tells us whatever the depth values, 3D points and projection matrices are, they have to fulfill this equation. And remember, in the two-view case, we were able to decouple things. We were able to decouple the estimation of the camera motion, which is in the matrix pi, from the structure estimation. Did you have a question?
Why is pi 3m by 3m size?
Yes, so that's a good question. I think it should be more than, I think this is not right, because these are matrices, so it should be 3 by 4. I think it should be 3 by 4m. I have to check. That's a good point. I think these dimensions are not right. Each of these matrices is yeah, this is not correct. Definitely, this is not right. So yeah, you're right. The dimensions here are not correct. For pi, you mean? Yeah. I have to check. There's an error here. The m should not be that. It's large. Yeah.
It should be 3 by m or over m.
Let's see. So pi is, I think, what was it? X is a 4D vector, so definitely it should be 3m by 4, I think. Yeah. So this is not right. 3m by 4, exactly. It is, yeah. Each matrix is 3 by 4, and so you have m matrices, and that makes it 3m by 4. So the question is, can we decouple structure and motion in the same way as we did for the two-view case? And in the two-view case, we had the epipolar constraint, and you'll see actually the derivations that follow now are quite an analogy to what we did in the epipolar constraint. We also had the projection equations that we started with. Remember, in the epipolar constraint, we said lambda 1 little x1 was large x, and then lambda 2 little x2 was large x, but rotated and translated. And we had these two equations for the epipolar constraint, and the way we derived it is we inserted that x in here, and then we applied certain transformations to remove the 3D parameters, to remove the x, this removes the x, but then we also were able to remove the lambda parameters. And we'll apply similar transformations to this matrix system, to this equation system. First of all, what we do is we stack together the projection matrices, pi, 1 through m, and this observation matrix, the image matrix, we called it I. So pi and I, we stack that together. Yes. And that gives us a 3m by m plus 4 matrix. Indeed, this pi matrix is a 3m by 4, and these are 3m by m, so that would be 3m by m plus 4. And so that's a fairly large matrix. And now the key idea is, if you look at this equation, it says I times lambda equals pi x. If we rewrite that equation, then we can write I pi times lambda and minus x equals 0, right? If you transpose, if you will. Because this is, if you just rewriting, it just says I times lambda minus pi x equals 0. And that's exactly the equation we have, which means there is a vector here, lambda and minus x, which is in the null space of this matrix. So it's just rewriting the same equation, and it says if I consider that matrix I pi, we call it NP here, this matrix I pi has a vector that is in the null space. So there is a vector, here it is, x minus lambda, that is mapped to 0. So sorry, I had I pi here, here's pi I, it's just a convention. And so the vector u, let's call it x transpose minus lambda transpose, that is in the null space of the matrix. So strictly speaking, if I have to first transpose these, then they are row vectors, then I can put them in a long row, and transpose makes a column vector out of it. And so this is a column vector which is in the null space of this matrix NP. And so, speaking in terms of linear algebra, you could say, if you consider, you could say the columns, sorry, there's a t too much, the columns of I and pi must be linearly dependent, meaning there exists a linear combination of these columns which is mapped to 0. And in particular, a non-trivial linear combination. Of course, if you take a 0 vector, that always is mapped to 0. But here we are saying there is a vector of 3D coordinate and non-zero lambda values that is mapped to 0, that is in the null space of this big matrix. And now comes the idea. The idea is that the fact that there is a non-trivial null space, I can express that fact by saying the rank of the matrix is smaller than the full rank. If you consider this matrix, since it is 3m by m plus 4, it has at most a rank of m plus 4. If all columns were linearly independent, the rank would be m plus 4. But what we are saying now is that the rank is smaller than m plus 4. There is a non-trivial null space, so there is a vector that is non-zero vector that is mapped to 0 by the matrix NP, and so its rank is at most m plus 3. Moreover, you will see later what we really want is that this null space should be one-dimensional, because you remember, just as in the epipolar constraint, we want a reconstruction that is unique up to scaling. Always there's the scale freedom. Unique up to scaling means up to scaling this vector should be the only solution that is mapped to 0. There should not be multiple different solutions, unless they're scaled versions of each other. And so we can say, in the case of a unique reconstruction, we want the rank to be equal to m plus 3. But in general, the constraint that there exists a solution, possibly non-unique, can be written as saying the rank of this matrix should be smaller or equal to m plus 3. If the rank is m plus 4, meaning this thing has a full rank, that means then there is no vector that is mapped to 0, and that means there is no solution to our equation here. And so, while in the two-view setting we have the epipolar constraint that couples the observations to to the camera transformations, here we now have a rank constraint on a matrix that contains, in some sense, the information that there should be a feasible reconstruction. There should be a 3D vector x and a vector of depth parameters lambda such that this vector is mapped to 0 by that matrix. And so we just use the projection matrix saying the solution should fulfill this equation system, and we can say this can only happen if the rank of that matrix is smaller than m plus 3. So we're already one step further. We now have a matrix and can say there exists a reconstruction if and only if the rank constraint is smaller than, if the rank is smaller than m plus 3. Unfortunately, this matrix still contains the 2D coordinates and the unknown camera parameters. Oh, actually, not unfortunately, this is interesting. It's a rank constraint on a matrix that only contains the 2D coordinates and the camera parameters. Much like in the epipolar constraint, here we have the 2D coordinates, here we have the camera parameters, here we have a similar constraint on the 2D coordinates and the camera parameters. There are no 3D parameters in there. Because all the 3D parameters, all the parameters containing the 3D information are in this vector u that defines the null space. Uh-oh. Yes. And so this is, in some sense, an analogon to the epipolar constraint for the multiview setting. And I must admit, it looks a little more abstract, especially if you're not so familiar with matrices and with rank constraints and conditions on the rank of matrices. But all it says is that the rank should be smaller than m plus 3. If it can be at most m plus 4, so it means there is a rank deficiency. It means there is a non-trivial null space, and that's all we're saying. And so you see that in a similar fashion to the epipolar constraint, we have now a constraint on the camera motion with the known 2D coordinates. What we now do is, it doesn't at a first glance look very much like what we did in the epipolar constraint, but once you go back to the epipolar constraint and check what we do for every image here, it actually is quite an analogy, you'll see. What we do is we try to compactify this, because it's not a very, I mean, this is a constraint, it is an informative constraint because the matrix has at most rank m plus 4, and now we say it should have at most m plus 3 if there is a meaningful reconstruction. But it's not very manageable because it's a very huge matrix and it has high dimensions, and then the constraint is not written in a very compact manner. And the question is if we can write it more compactly, and it turns out that yes, we can do that. So we take this matrix NP and we apply another matrix which is I orthogonal. So that is the image matrix orthogonal, and what we have here is x1 hat, x2 hat, xm hat. And if you go back to the epipolar constraint derivation, at some point in the derivation of getting from the projection equations to the epipolar constraint, we also multiplied with xi hat. Actually, there we multiplied with t hat, but it's a bit similar that we multiply with a matrix in order to transform the constraints. And these are the skew symmetric matrices associated with the 3D with the 2D coordinate vectors x1 hat to x1 to xm. The property of this matrix, you remember x1 hat is nothing but the matrix that models the cross product with x1. And so one of its properties is that if I apply xi hat to xi, it gives me 0. This is 3 by 3 skew symmetric matrix that has rank 2 and it has 2 columns vectors that are both orthogonal to xi itself. And so if you apply matrix I orthogonal to the image matrix I, you get 0. Because you just multiply xi hat by xi, and so you get 0. Which means if we multiply this to this matrix, so we had np times x and minus lambda equals 0. Let me write that down. np times x transpose minus lambda transpose equals 0. And now if we multiply from the left with I bar, np is this matrix. If we multiply this with I bar, we get I bar times pi, and I bar times I is 0. So we end up with the equation I bar times pi times x equals 0. It's actually a little bit simpler if we go back 2 equations, multiply this equation with I bar, you get 0 on the left-hand side, the lambda parameters disappear, and you get I bar times pi times x equals 0. And this is to some extent analogous to the epipolar constraint, where also we kicked out the lambda parameters in the derivation. And here you kick them out by multiplying with I bar. And so we get this equation. And what that equation basically says, we now have a matrix I orthogonal times pi, and x, the 3D coordinate vector, is in the null space of that matrix, quite simply. And so it says if we want a meaningful reconstruction, a consistent reconstruction for the multiview setting, this matrix I orthogonal times pi, it should have a non-trivial null space. The 3D coordinate vector in homogeneous coordinates, so always 4 components, is in that null space. And this matrix, we call it WP, so I apologize, you see there's a lot of matrices that now come in. One is called NP, one is called WP, but it's just trying to rewrite these multiview constraints in a compact manner, as compact as possible. And so now we have this matrix. If we look at it, this matrix is a 3m by 4 matrix. And so the rank of this matrix is at most 4. But now the constraint says there should be a non-trivial null space, and that implies if there is a vector that is mapped to 0, some non-zero vector that is mapped to 0, it means the rank is deficient, it means the rank can be at most 3. And so you see, in contrast to the previous constraint, this is a simpler constraint. We have a matrix that has at most rank 4, because it has it's a 3m by 4 matrix, and now we say the rank is bounded. It has at most rank 3 if there exists a meaningful reconstruction. And the idea is then again, you want this null space to be unique. You want a one-dimensional null space, which means a reconstruction that is unique up to scaling. And we have that if the rank is exactly 3. If it's exactly 3, it means the null space is one-dimensional. It means we have a unique reconstruction. If the rank is smaller than 3, so 2, 1, or 0, then we have a non-trivial, then we have the case of a non-unique solution. And so you can, but just by constructing this matrix and studying the rank of that matrix, you see all the possibilities. If there is no solution to the problem, the null space is just the 0 vector. That's the case if the rank is 4. This can potentially have rank 4, this matrix. If the rank is 4, there exists no reconstruction. If the rank is exactly 3, there is a reconstruction that is unique up to scaling. And if the rank is smaller than 3, 2 or less, then you have non-unique reconstructions. And so we have the rank of WP should be smaller than 3, or we can say the rank of NP minus M should be smaller than 3. This is a rank constraint for points observed in multiple images. We can do the same approach for lines. The reason why we do that is that for lines, interestingly, if you consider observing a 3D line in multiple images, observing it in 2 images is not very informative, in the sense that there always exists a pre-image. If I observe 2 lines in 2 images, then there always, no matter where the 2 lines in the image are, there always exists an intersection of these planes that define the pre-image. And so for 2 observations of a line, you always have a consistent reconstruction. So it's hard to get meaningful constraints for the case of lines once you only consider 2 images. But if you consider multiple images, then you have a non-trivial case. Let me see if I have an image. Here is an image. If I observe lines in 2 images, they always intersect somewhere, no matter where I observe them, no matter what camera transformation I consider, there's always an intersection. So saying find a camera transformation between my 2 images such that the pre-images intersect in a line, that's not a helpful information, because no matter what camera transformation I consider, I always have an intersection. But we'll see once we have 3 images and say we want camera transformations from the first to the second camera and from the second to the third camera such that all these 3 planes intersect in a line, that is no longer a trivial constraint. That means you do have to have a meaningful camera transformation if you really want all 3 planes to intersect properly. And so this is the case we will consider now, the case of line features and how we tackle that in a rank constraint. We saw it already. The way we phrase the lines is we define the line, all points large x on that 3D line, we parameterized with a base point x0 plus some scalar offset mu times a vector v. And if we work in homogeneous coordinates, the last component of v is 0 and the last component of x0 is 1, right? So that all x have homogeneous coordinates. And so then we already found in the last lecture that we have 2 constraints in the case of a line observed in an image I. So I is now the index of the image. Here's the projection matrix into image I, pi I. And we saw that there is 2 constraints, one for the base point of the line, x0, and one for the vector x. And what we saw is that Li was the vector that defines that pre-image, that is the normal vector on the plane. Here you see it. This is Li. And we say for any point x, we know that if I project it into the image I, then that vector is orthogonal to this vector Li. So in other words, Li, where is it? Li, for the base point in particular, if I project that base point into image I, so this would be little xi, then it's orthogonal to Li, to this vector spanning the pre-image plane. And that holds also for all other points on the line, and so in particular it holds for this vector v. And so we have these two constraints for the line observed in an image, I, and we see that they are such that there's two constraints, two vectors that live in the null space of this matrix. And if we then stack all these constraints for each image into a large matrix, so this would be an M by 4 matrix, then we can say it's an M by 4 matrix, so the rank of this matrix is at best 4. Now we say we have two independent vectors in the null space. They are definitely independent because this vector has the last component 0, this has the last component 1, so they're not linearly dependent, the two vectors that live in the null space. And these two vectors are mapped to 0 by that entire matrix. So if I apply that matrix to x0, I get 0. If I apply the matrix WL to V, I also get 0. And so I know there is two non-trivial, independent, linearly independent vectors that live in the null space of this matrix. And that tells me that the rank of this matrix, if I have a consistent reconstruction, then the rank must be less or equal to 2. It is rank deficient. It can have at most a rank 4. If the null space is two-dimensional, then the rank must be 2. And so here you can see how we can use rank constraints and how we can use these to impose our constraints, to say a consistent reconstruction exists if and only if these matrices are rank deficient. Rank deficient means they don't have full rank. Full rank here would be 4. And here we say the rank must be at most 2 if there exists a consistent line. And now maybe one more comment how you can easily see why for lines we need more than 2 images to have a meaningful constraint. M, little m, is the number of images here. If we take 2, then we have a matrix that is 2 by 4. A 2 by 4 matrix has at most rank 2, right? And then saying, oh, the matrix should have at most rank 2 doesn't really tell you much. If you see the rank is 2 by 4, then you know just by looking at it, a 2 by 4 matrix can only have at most rank 2. And so you see this rank constraint becomes non-trivial only if M is larger than 2. Otherwise, it's always fulfilled. Any 2 by 4 matrix has at best rank 2. So it doesn't tell you anything about the structure of the matrix. The idea is we want to use this rank constraint to tell us something about these projection matrices, something about the camera motion. If we take 2 images and say, oh, then we have a 2 by 4 matrix and say the rank is at most 2. Yeah, any 2 by 4 matrix has at most rank 2. So there's no information, whereas information enters in this constraint, by this constraint, for m larger than 2, 3, 4, 5. And then it becomes an interesting constraint. Then it is no longer trivial. Maybe a geometric interpretation. We now saw rank constraints for these matrices that are called WL for the case of lines and WP for the case of points. And we saw that the rank constraint tells us something about the existence of a pre-image. This is why I call this section from pre-images to rank constraints, because it is the rank constraint that tells us there exists a pre-image. What I want to show you now is the geometric interpretation of these rank constraints. Let's go back to the case of a point. So we consider a 3D point, large X, that we observe in M images. And then we had this matrix WP. Here it is again. X1 had pi 1, X2 had pi 2, etc. up to Xm had pi m. a matrix containing the 2D coordinates and the camera motion, and we said the vector x is in the null space of that matrix. It is mapped to 0. All these matrices xi hat, these are the skew symmetric matrices formed by the 2D coordinate vectors. They're 3 by 3 matrices that all have rank 2. Remember, skew symmetric matrices always have an even rank. So the 3 by 3 matrix can have rank 2 or rank 0. 0 only if it's a 0 matrix, which means then you have only a 0 coordinate vector, which, since the third component of these xi's is always 1, it's not possible. So these have exactly rank 2. And so the rows of this matrix define a set of 2m planes. Because wp times x equals 0 means that the point x is in these planes, right? If I have a vector that say v transpose large x equals 0, it means that x is orthogonal to v. That means that if v is the normal on the plane, it means x lives in that plane. And here basically we have a set of m planes that are defined by these, two m planes. There's 2 linearly independent rows that each matrix here contributes. So we have 2m planes, and wp equals 0 means that the point large x is in the intersection of these 2m planes. And in order for the 2m planes to have a unique intersection, we need to have that the rank is 3. Remember, the rank can in principle be 4. A unique reconstruction, a unique intersection of these planes is obtained if the rank is 3. If it's smaller than 3, then there is an intersection, but it's no longer unique. Here's the idea. Here's the point observed in this case 2 images. Each image contributes 2 planes, and now we say the 3D point is in the intersection of these planes, and so here's the 3D point, and so this is how you can visualize what the matrix WP implies. It's a matrix that says the 3D point should be in the intersection of 2m planes. If we have 2 images, these are 4 planes. And that is indeed a non-trivial constraint. Right? If I had a different camera motion, then there would be no intersection at all. If we consider the case of lines to give you some geometric interpretation to this rank constraint, here I show it again. This is the matrix WL for the line. Let's first consider 2 views. So WL looks like that. L1 transpose pi 1, L2 transpose pi 2. And we say there are 2 independent vectors that are in the null space of this matrix, namely the base point x0 and the offset vector v. They are both mapped to 0 by this matrix, and therefore the matrix has not rank 4 but rank 2. But as I said, in the case of 2 lines, a line observed in 2 images, this is a 2 by 4 matrix. So the constraint rank smaller or equal to 2 is always fulfilled, no matter what camera motion you consider. But as I said, once we consider more than 2 images, 3, 4, 5 images, this becomes a meaningful constraint. Here's an example. For the case of lines, no matter what lines I observe, if I observe a line here, then that spans this pre-image P, this plane here, and then no matter what line I observe here, L or L2 or L2 prime, there always is some intersection. So there's no information considering lines in two images. And geometrically, the fact that the matrix is a 2 by 4 matrix basically says there's always a null space of dimension 2. There's always an intersection. What we do now is we try to compactify yet more these rank constraints, and we get to what is called the multiple view matrix. So whereas NP and WP didn't have names, the matrix that we derive now is actually has a name. It's called the multiple view matrix, and so this is then the most compact form to express the multiple view constraints. What we do is we go into the coordinate system of the first camera. As I mentioned, that is what you typically do. So pi 1 is then a matrix 1, 0. Then I have pi 2 to pi m are the matrices containing rotation and translation. We write them somewhat compactly in this fashion. There are different ways to write these projection matrices. This is a notation that is, for example, propagated also in the book of Hartley and Zisserman. Once you have a non-calibrated case, this is just a side remark. Typically we work in a calibrated setting, but if the camera is not calibrated, so the intrinsic parameter matrix is not the identity, then basically you have such projection matrices, but Ri, they still have the same form, except that Ri is not going to be an orthogonal matrix anymore, but an arbitrary invertible matrix, because this matrix K is multiplied to it, and K is always invertible. We had the matrix WP, here it is again, and we saw that 3m by 4 matrix, and for the case of points, we said that the rank is at most 3. There is a non-trivial null space to that matrix. Now what we do is we take this matrix WP and we multiply it by this matrix. It's a bit strange at the first glance why you would multiply by the matrix DP, but I'll show you in a second why we do that. Actually, it's not difficult to see. For WP, we have a 3m by 4 matrix and say the rank is at most 3. And what we get here is a matrix called MP, that is a 3m times m minus 1 by 2 matrix. So it has 2 columns. And the rank is at most 1. So the constraint here says this matrix has 2 columns, and the 2 columns are linearly dependent. And this is, of course, a little bit simpler if you, rather than saying I have a matrix with 4 columns and they're linearly dependent, here saying I have 2 columns which are linearly dependent is somewhat simpler. It basically means that one column is a multiple of the other column. How do we get to this matrix called MP? We take the matrix WP and multiply by this matrix. What's important now is that this matrix is a full rank matrix. Why is it full rank? It's a 4 by 5 matrix, so the rank of that matrix is at most 4. And if we look at it, we see there's 2 columns that are linearly independent in x1 hat. The third column is x1, and then the fourth column is this one that has a 1 down here, so it's also linearly independent. So we have 4 linearly independent columns here. And so you can show that this is a full rank matrix, and now we make use of a property that we mentioned in the linear algebra setting. We said that if you take a matrix and multiply it with the full rank matrix, then it doesn't affect the rank. So let's look at what that says here. For this case, we take the matrix WP, we multiply by dP, and you can try this at home. If you multiply it out, you get this matrix here. And then you can show that that the rank constraint on WP, saying the rank of WP should be at most 3, this can hold if and only if that submatrix down here has a rank less than 1. Why is that? Because this contributes a rank of 2, and clearly since you have 0 and 0 here, it's linearly independent from the remainder here, and that means this submatrix can only contribute one more linearly independent row. See, you have 2 linearly independent rows here, and this whole remaining matrix can only contribute one more linearly independent row. And so you can deduce that this submatrix that we have down here, I've rewritten it here, MP is a matrix that has at most rank 1. It's a matrix containing 2 columns, and saying it has rank 1 basically tells you that these 2 columns are multiples of each other. And this is why we reformulated the rank constraint with this matrix MP to have an as compact as possible representation of the constraints, which says there are 2 columns in the matrix and these are multiples of each other. So to summarize what we now found out, and I admit it's a bit complicated, it's a bit involved. There's a number of constraints, but they basically contain the information from the multiple views. They tell us, is there a consistent reconstruction for a given camera motion? It doesn't tell us what the reconstruction is, it just says there exists a reconstruction, a feasible reconstruction, if these rank constraints are fulfilled. So we know there exists a feasible reconstruction if and only if these rank constraints are fulfilled, and you can write them in many ways. The first constraint, we had the matrix NP saying that NP had a rank that was smaller than M plus 3. Then we had the matrix WP where we said this matrix has 4 columns, but really it's only rank 3, at most rank 3. And now we have this multiple view matrix MP up here, where we can say the rank of this matrix is at most 1. It has 2 columns, so it can have rank 2 in principle, but for a reconstruction to exist, we need it to have rank 1. So this is all I wanted to say about rank constraints for points, or this summarizes basically what we found, how we can encode this multiple view reconstruction, the existence of a reconstruction in terms of ranks. And in fact, we'll see in a second, once we consider this matrix MP, it has 2 columns. So for that matrix, it really only has there are 3 possibilities. It can have rank 2. Then there is no reconstruction. It can have rank 1, then there is a unique reconstruction up to scaling, and it can have rank 0, which means it's the 0 matrix, and then there's no longer a unique reconstruction. So there exists a reconstruction, but it is not unique. Again, we can interpret that matrix geometrically. This is the matrix MP, 2 columns. The constraint that the rank is smaller or equal to 1 implies that the 2 columns are linearly dependent, and it says there is a vector, and in fact this vector is lambda 1 that is mapped to 0. You can check that if you insert lambda and 1 here and multiply with the matrix, what you get is these constraints. And what this constraint reads, it just says there must be a consistent depth value, lambda 1, of this point such that all these equations are fulfilled for the other images. And so this is interesting because the constraint that MP should have rank 1 basically says nothing but the fact that there should be a consistent depth value. The exact information that is missing in the reconstruction, the depth from the first camera, there must be one depth value such that for all images this is fulfilled. So in other words, this multiple view matrix encodes or captures exactly the information that is missing in the reconstruction from a single image, but that is encoded in the multi-image scenario. And so this one vector living in the null space of that matrix, this is the one lambda and 1. Now, how does that relate to the epipolar constraint? Not surprisingly, I mean, we are now considering the multiview setting, so we have multiple images of points or lines, and in the case of points, once we boil things down to the two-view setting, we should see the epipolar constraint emerge. And we can see that the multiview matrix also has the epipolar constraint built in, so to speak. The constraint that this has rank 1, exactly rank 1, so a unique reconstruction, says that this should be a multiple of that. So this column should be a multiple of that column, and more specifically, it says that xi hat ti and xi hat ri x1 should be linearly dependent. So the fact that these columns are linearly dependent implies that separately each of these should be linearly dependent with each of these. And that linear dependency of xi hat ti and xi hat ri x1 leads to the epipolar constraint. So at that point you would say, oh, then the multiview constraint here, the rank constraint on this multiview matrix contains nothing but the epipolar constraints. But actually this is not true. So this is, by the way, the epipolar constraint between the first image and the eyes image. So in the multiview setting we have m images, and so in principle we could tackle the problem of multiple views just by taking 2 views at a time and having a constraint between the first and the second image, between the first and the third, first and fourth. And what we'll show in a second is that the multiview constraint contains, among other things, the epipolar constraints from the first to the other images. But it contains, we'll see in a second, it contains more than that. Because it's not only that this is a multiple of that, so these are linearly dependent, but in addition we can say that the scale factor that models this linear dependency, that says one is a scaled version of the other, must be the same for all of these structures. And this is the additional information that we have here. So it's not just that this entry is a multiple of that entry, and this entry here is a multiple of that entry, but they must be the same multiples. There is one, so the whole column is a multiple of that whole column. So I want to show you now that this leads to the epipolar constraint, that the epipolar constraint is basically one sub result of this rank constraint. So we said xi hat ti and xi hat ri x1 are linearly dependent. And we said that this gives rise to the epipolar constraint. And this can be proved, so we assume that the two vectors xi hat ti and xi hat ri x1 are dependent. So there exists a scalar gamma such that one is a multiple of the other. Right? Linearly dependency basically means that some linear combination of the two gives 0, a non-trivial linear combination, and so that in this case can just be rewritten by saying one is a multiple of the other, a scalar multiple of the other. Now since xi hat ti is xi cross ti, the cross product of xi and ti, this is a vector that is proportional to the normal on the plane spanned by xi and ti's, right? So I have xi and ti, and this vector is proportional to the normal on that plane. Similarly, xi hat ri x1 is proportional to the normal spanned by xi and ri x1. Same argument that this is the cross product of xi with ri x1. And the linear dependency of the two is nothing but saying that the three vectors xi, ti, and ri x1 are coplanar. So if I take the plane spanned by xi and ti, the normal vector on that plane is proportional to the normal vector on the plane spanned by xi and ri x1. And that can only be if and only if these three vectors define the same plane. They live in the same plane. And so we have the constraint that xi, ti, and ri x1 are coplanar. And coplanar means that this product here, cross product times the vector, is 0. That's saying the same thing. That if I take the three vectors and do this triple product, we had it before, then it's 0, meaning the volume spanned by these three vectors is 0. And if you go back to the epipolar constraint, this is actually nothing but this epipolar constraint. So it's a bit strange that, but not surprising, the epipolar constraint is contained in the multiview constraint. So in other words, we can derive the epipolar constraint from the multiview constraint. But there is more in it. So considering multiple views is more informative than just considering pairs of images. So we not only get the epipolar constraint, but we get more. If we take this multiview matrix, it's a matrix, as I said, with two columns, and now I'll write the two columns in this fashion. And we are saying the rank of this matrix that has two columns is rank deficient, so it has at most rank 1. And there is now a property that I'm not going to prove because it's a little bit involved, but for such matrices, and I must say it's quite amazing what kinds of things you can prove about matrices, and people have done that in linear algebra, and so we can use this expertise. For such matrices, one can prove that the rank is deficient if and only if these constraints are fulfilled. AI times BJ transpose minus BI times AJ transpose is 0 for all I and j. So as I said, we're not going to prove this statement, but it means that the rank constraint on this matrix saying the rank is less or equal to 1 is equivalent to a family of constraints of this type. AI BJ transpose minus BA AJ transpose is 0. And if we insert the exact values of A and B from the multiview matrix, these are the constraints we get. So they are a bit involved, I admit, but these are the constraints that we can get, and then we can extract xi hat, that's on the left side, and xj hat on the right side, right? If if you multiply these transpose out, you get T transpose xj hat transpose. Similarly here, you can extract the xj hat on the right side. And these are, so in other words, we have this constraint set for all I and j, and that is equivalent to the multiview rank constraint. So whereas the epipolar constraint, the pairwise epipolar constraints fall out as a side result from the rank constraint, they're not equivalent. But what is equivalent to the rank constraint are these so-called trilinear constraints. And these are constraints, if we look at them, they couple information from the I's image, the J's image, and the first image. Right? So these are constraints that always couple three images. And this is, I must admit, somewhat surprising at the first glance, that if you consider M images, you can show that the constraints you get from M images are not equivalent to the constraints for pairs of images, but they are fully captured in so-called trilinear constraints, constraints that couple three images always. And so this equation that we have here is a matrix equation that has 3 by 3, 9 scalar trilinear equations. And only 4 of them are linearly independent. So there's 4 equations really in this matrix system here. And so we get 4 scalar linearly independent, 4 linearly independent equations for triples of images, where we consider image 1, image I, and image j for all ij. That is interesting, and it's a non-trivial result that we don't need to consider quadruples of images and constraints among 4 images. It turns out that constraints among 3 images are sufficient. And now we can get a little more into how do these trilinear constraints relate to the epipolar constraint. So here are the trilinear constraints again. And what they say is, as long as these entries xj hat tj and this one are non-zero, it basically means that the vectors xi hat ri x1 and xi hat t are linearly dependent. Of course, there is a possibility that what's in the brackets here, these expressions themselves are 0. That can happen, but this is what's called a degenerate case, and that's the case if the point P lies on the line through the optical centers OI and OJ. I think I have images of this. So there's a lot of pathological cases for reconstructions of points from multiple images. If the points are in a nasty sort of position, then we don't get useful constraints, but in the non-degenerate case, these are very informative cases. So in other words, except for degeneracies, the bilinear epipolar constraints relating two views are contained in these trilinear constraints. Because again, the fact that this vector, the two vectors, xi hat r x1 and xi hat ti are linearly dependent, this is the epipolar constraint. Of course, I just showed you that the rank constraint, the multiview matrix having rank less or equal to 1, is equivalent to bilinear and trilinear constraints, epipolar constraints, and constraints cupping triples of images. This equivalence holds only in the case that MP is non-zero. If the matrix MP is 0, that can in principle happen in certain degenerate cases, then this equivalence is not there. We saw that the multiview constraint, the rank constraint on the multiview matrix, saying this matrix MP should have rank at most 1, can be rewritten with bilinear and trilinear constraints, and these constraints can be used to assure the uniqueness of the pre-image of a point. So we observe a point in 3 images, and we want a unique pre-image. Yes, I think this is getting a little bit too technical. I think at this point I'm going to skip this part. This is results that I'm not going to prove anyway, but I'll rather focus on the applications. If you want, you can go through the slides and read that part yourself, but I'm going to skip it for now. And I'll consider some degenerate cases because that is helpful to understand the reconstruction problem, to see what reconstructions we can get and where reconstructions can fail. This is a case where I have a point observed in 3 images, and then I say I want a consistent reconstruction. And the interesting thing is, if you consider 2 images only and say for each 2 images I want a consistent reconstruction, then this would be a feasible solution, in the sense that if I observe that point then basically for any 2 images these lines do intersect somewhere if they're all coplanar. So I'm considering a camera where all rays to the points actually are in the same plane. It's called the trifocal plane. So the optical centers of the cameras, the point P lies in the plane spanned by these optical centers. And if that happens, then you can clearly see that for any 2 lines, x1 and x2, for example, there is an intersection. For x1 and x3, there is an intersection. And for x2 and x3, there's also an intersection. For all pairs of observations, I have a meaningful intersection, but there is not a consistent 3D reconstruction. There is not a unique point that lies in the intersection of all 3. And so this is a rather degenerate case, of course, where the point I consider lies in that plane spanned by the 3 optical centers. In practice, if you do reconstruction from image data, this is not going to happen. But in theory, it could happen, and this would be one of these degenerate cases. It says here it arises rather seldom. A degenerate case that is not as seldom but actually happens somewhat frequently is the case that the optical centers all lie on a line. That happens, for example, if you want to do a very important application scenario, if you want to do reconstruction from a driving car. So you drive with a car down the road, and then you take images, but if your car goes straight, then all these optical centers are on a line. So it's called a rectilinear motion. And then I observe points, and in that case again, all pairs of lines may intersect without the pre-image being unique. So you see here, the intersection of these two gives a point, the intersection of these gives a point, and so for all pairs of images, this gives a constraint. And this is a degenerate scenario where the epipolar constraints, if you only consider pairs of images and say, I want an intersection of these rays, I want there to be a consistent 3D point, then you will get consistent 3D points. In fact, you'll get 3 different consistent 3D points that are always pairwise consistent, but they're not consistent for all 3 images. So meaning the point P, there is not a single point P that is consistent with all 3 observations. And this is an interesting scenario where actually the trilinear constraints do assure a unique pre-image. So this is a case where using the multiview constraint and the equivalent trilinear relationships helps you. It gives you more information than just considering pairs of images. So this is a practical case that can happen in the real world, and that happens every now and then, a case where just considering 2 images is insufficient, but considering 3 or more images helps. And in fact, we saw that considering triples of images is sufficient because it's actually equivalent to the multiview constraint. So to summarize what we've learned about the observation of points in images, we constructed a multiview matrix, we called it MP. That matrix has 2 columns, and so it's a matrix of rank at most 2. And then there are 3 possible cases for this matrix. Either it has the full rank, rank 2, then there is no consistent pre-image. That means there is no point correspondence and the pre-image is empty. There is no intersection of the pre-images. There is no consistent reconstruction. The case that the rank is 1, we have a point correspondence and we have a unique pre-image. And then the case that the rank of the matrix is 0, and that means we have point correspondence, but the pre-image is not unique. There are multiple solutions. Not just up to scaling, but the whole null space is higher dimensional, not one-dimensional. One thing you should keep in mind, if the rank of this matrix is 0, it means the matrix itself is 0. A matrix with 0 rank is a 0 matrix. And so, of course, in practice, in the reconstruction scenario, you want to put yourself in the second case, in the case of rank 1. You want a reconstruction that is unique. And so you want a camera transformation among the different images from one camera to the next in such a way that this multiview matrix has exactly rank 1. And one thing you can do, of course, is when you actually compute feature correspondence. Remember, at this point, we were always working under the assumption that we have correspondence between points in different images. One of the things we can do is we can always construct the multiview matrix and put points into correspondence in such a way that the rank condition is fulfilled, that the matrix MP is rank 1. So in principle, we can use these constraints to establish point correspondence. So we could do something that we already talked about in the two-view setting that led to what was called the bundle adjustment. We could use the rank constraints for the reconstruction problem. The rank constraints always tell us if there is a consistent reconstruction and a unique reconstruction up to scaling if and only if the rank is 1. And so we could use an optimization process where we estimate and minimize a global objective function under the constraint that the rank condition is fulfilled. And that would lead to a nonlinear optimization problem, quite an analogy to the bundle adjustment for the two-view setting. The alternative to bundle adjustment is to separate and decouple structure and motion. So you remember in the class we talked about these two strategies to do structure and motion. One is to try to estimate everything in one, doing bundle adjustment, some nonlinear optimization. We said that's difficult because these energies are not convex, and so it's hard to compute minimizers. The alternative is the one that we proposed in the 8-point algorithm, and that is that you separate structure and motion. First estimate motion of the camera, and then estimate the structure. And what I will show you in the following slides is that reconstruction algorithm using a separation of structure and motion. One should say that this approach doesn't necessarily lead to a practical algorithm. I mentioned that before. This is a difficulty in the whole reconstruction domain, that you can do nonlinear optimization, but it's hard to compute solutions because you have a non-convex energy. On the other hand, you can do structure and motion decoupling. You can estimate camera motion first using, say, the 8-point algorithm, and then estimate the structure. But the 8-point algorithm isn't typically optimal in the context of noise and uncertainty because you're not minimizing the reprojection error. Spectral approaches, by the way, means we use singular value decomposition, as in the 8-point algorithm, to estimate the camera motion. So let's look at how that how that works. It's called a factorization approach because we decouple or factorize this problem. So we assume we have m images of n points. We have the rank constraint. That rank constraint, I wrote it here, means this matrix containing these two columns has rank 1, and that means that the linear combination of these two columns is 0. And so we can say that there is a parameter alpha j. We observe j points, n points indexed from 1 through n. J goes from 1 to n. So for each of these points, here's the j, we have such a constraint with a parameter alpha j. And if you look at the individual rows of this equation system, you can obtain these rows also by looking at these projection equations, right? This is the projection equation coupling the projection of the point in the first image and the point in the J's image. Sorry, in the I's image. Point J in the first image, point J in the I's image, and this constraint couples the two. And if you multiply by xij hat, you get this equation. And so, in other words, what you see is that this scaling factor alpha j that models the linear combination here is nothing but lambda 1 over lambda 1j. That is the depth of the j's point in the first image. This is what I said earlier already, that this linear combination basically encodes the fact that there is a consistent depth with respect to the first image. Here you see it again. So basically that parameter alpha is nothing but the inverse depth, if you will. I think at this point I will stop for now because it's been rather intense. You've seen a lot of matrices, a lot of rank constraints today. I apologize that it was a little bit technical. So next time we'll talk about how to do a reconstruction algorithm with these constraints. Thank you.